The most exciting thing is about to happen in cosmology. The James Webb Space Telescope is ready to be launched. It's a $10 billion high-tech wonder that will explore strange new worlds and search for life in our galaxy and beyond. We might be on the edge of finding the answer to the biggest question in science. Are we alone in the universe? Now, get ready to find out how this first light machine will change the way we see the universe and show humanity things it's never seen before. Named after NASA's second administrator who led the Apollo missions and was responsible for more than 75 launches into space during the 60s, the James Webb Space Telescope, also called Webb or JWST, is the largest space telescope in history, and it's optimized for infrared wavelengths. It will complement the Hubble Space Telescope's abilities and extend our discoveries of galaxies and exoplanets that could have life. The Hubble telescope created a revolution in astronomy and raised new questions that required a new, different, and more powerful telescope to be built. The Webb telescope is 100 times more powerful than the Hubble and will have longer wavelength coverage and greatly improved sensitivity over any previous space telescopes. This is why some scientists call it a time machine, because the longer wavelength coverage will allow the telescope to look further back in time to find the first galaxies and stars that formed in the early universe. Helping with this incredibly difficult task is the lightweight, deployable primary mirror, which is 2.7 times larger in diameter than Hubble's mirror. That's about 6 times larger in area. The mirror is made of a special material called beryllium, which has a high strength-to-weight ratio. This will give the JWST more light-gathering power over other space telescopes. These special beryllium mirrors are coated with a super thin layer of gold that's about 1,000 atoms thick to optimize their reflectivity in the infrared spectrum. The entire amount used to coat all the mirrors is a little more than the mass of a golf ball. Unlike the Hubble Space Telescope, the James Webb Space Telescope will operate much farther from Earth, allowing it to achieve an extremely cold operating temperature, stable pointing, and the JWST will have a much higher observing efficiency than the Earth-orbiting Hubble. The JWST is designed to detect near-infrared and mid-infrared wavelengths. This is the light beyond the red end of the visible spectrum, which is invisible to the human eye. For this to happen, the optics need to be freezing cold. For example, this image shows the comparison of the Carina Nebula in visible light on the left and infrared light on the right. In the infrared image, you can see more stars that aren't there in the visible light image. The James Webb Space Telescope will have a mission lifetime of around 10 years, and that lifetime is ultimately limited by the amount of fuel the telescope needs to maintain its orbit and the proper function of the spacecraft itself and its instruments. The high-tech infrared detectors need to be cooled with liquid helium to prevent thermal fluctuations from swamping the astronomical sensors. Because the helium will gradually be used up, this expensive telescope only has a short mission life of 5.5 to 10 years. So chances of it operating beyond this will depend on a manned spaceflight, which could happen 10 years from now, but there's nothing planned as of yet. Which brings us to the next point. The launch of the James Webb Space Telescope will be a huge leap of faith for humanity and our technological capabilities. The reason is because Webb will be operated at the second Sun-Earth Lagrange point, which is located approximately 1.5 million kilometers away from the Earth. This means it cannot be repaired or serviced, including refilling its liquid helium tank after reaching its destination, and will be beyond reach of any currently planned crewed space vehicle. Some have asked why Webb cannot be assembled and tested in Earth's orbit, but this was studied and found nearly impossible to pull off. The International Space Station and its crew do not have the capabilities to assemble precision optical structures in orbit. There is also the problem of space junk and debris, considering that China and Russia recently blew up satellites in space. This floating debris could damage or contaminate the expensive telescope's optics. Not only that, but if the space station were to be used as a stopping point, another rocket would be needed to launch Webb to its final destination, and the observatory would have to be designed with much more mass to withstand a second launch. It's fragile enough as it is. The James Webb Telescope is bigger than Hubble, with the most important thing being the diameter of the primary mirror, which is made up of 18 hexagonal segments and stretches 6.5 meters from top to bottom, with its total area measuring slightly more than 25 square meters. The JWST weighs in at approximately 6,500 kilograms. That's a little more than half of what Hubble weighed on Earth. The largest structure of the JWST is its sun shield, which protects the deployed primary mirror, and the tower that holds the secondary mirror, which is also made of beryllium and is gold-coated. You'll notice something different about the Webb telescope, and that is its open design. The Hubble is enclosed in a tube, but since Webb will be farther from the heat of the Sun, Earth and Moon, its open design and special heat shield will keep it cool enough for its infrared detectors to work properly. This sun shield is about the size of a 20-car parking lot and has 5 layers of special material called Kapton, which is also used in spacesuits. Each one of these is about as thick as plastic wrap and is coated with aluminium to help keep the telescope as cold as it needs to be to detect infrared light. Each layer of the sun shield is separate from each other, and each one is cooler than the one below. Heat radiates out between the layers, and the vacuum between each layer is also an efficient insulator. It works so well that one side of the shield that faces the sun will be 85 degrees Celsius. The other side, where the telescope, mirrors, detectors and filters are located, will be a chilly -233 degrees Celsius. To make observations in the infrared spectrum, the JWST must be kept under 50 Kelvin, otherwise unwanted infrared radiation would overwhelm its instruments. Even infrared radiation from the telescope itself can cause problems, but the liquid helium cooler on board will take care of that. All warm bodies and objects emit infrared radiation, even you and I. Being able to observe in infrared light wavelengths means the Webb can detect more distant and older objects in the universe. If you want an idea of how sensitive the JWST will be, one project scientist said it's so powerful it could probably detect a bumblebee on the Moon from Lagrange Point 2. Of course, it would take a timed exposure to get something that small and sensitive, and the bumblebee shouldn't move. But this isn't a problem when looking at distant objects in the universe, because they look as though they're standing still. Now, the JWST will communicate with scientists on Earth using a high-frequency radio transmitter. NASA's Deep Space Network, which consists of large radio antennas, will receive the signals, and those will be sent to the Webb Science and Operations Center at the Space Telescope Science Institute in Baltimore, Maryland, USA. Now, the James Webb Space Telescope is finally set to launch. There'll be a month of critical maneuvers as the telescope cruises deeper into space, and some call this 29 days of terror. These 29 days will be a real intense time, because a lot of important stuff needs to happen. But the first thing is getting it safely into space. The gigantic size of the Webb telescope presents a huge and unique challenge. It's not easy to send a telescope this big into space, especially since an Ariane 5 can't carry anything broader than 5 meters wide. This is why the telescope had to be designed like a gigantic, high-tech, billion-dollar piece of origami. This includes the tennis court-sized sun shield, which will be folded up for launch, put inside the Ariane 5 cargo capsule, and then unfolded once it's in position. All of these were amazingly difficult engineering problems, and here's the real mind-blower. The James Webb Telescope will have 50 major deployments, involving 178 release mechanisms to deploy those 50 parts, and every one of them must work. This mission is like nothing we've ever attempted before, and it will be, hands down, the most complicated space activity we've ever done. This is how the launch mission will go. The Ariane 5 launch vehicle will provide thrust for approximately 26 minutes after morning liftoff from French Guiana on December 18, 2021. Just moments after the second stage engine cutoff, Webb will separate from the Ariane rocket, which will trigger its solar array to deploy so it can begin producing electricity from the sun. The telescope will quickly establish its ability to orient itself and fly in space. For the telescope to turn, the JWST will use 6 reaction wheels to rotate itself. These reaction wheels are basically flywheels that store angular momentum. Those reaction wheels will work in combination with 3 star trackers and 6 gyroscopes that provide feedback on where the telescope is pointing and how fast it's turning. This will help keep the solar array pointed at the Sun and the high-gain antenna pointed toward Earth. But while it's on the way to its L2 target, some important things need to happen. Webb will make a mid-course correction towards the second Lagrange point. The telescope will be on a direct course to the L2 target and will not orbit the Earth. During this time, there'll be a small but important trajectory correction maneuver that will use small rocket engines on board the JWST itself. The high-gain antenna will also be quickly deployed to enable communications with the satellite. At this time, the telescope will be moving so fast that it will pass the Moon's orbit in 1.5 days. That's half the time it took the Apollo astronauts to reach lunar orbit. After this, a second trajectory maneuver will be executed, and the sun shield will be deployed, starting with the fore and aft sun shield pallets. The next step is the separation of the spacecraft bus and telescope by extending the telescoping tower between them. This tower will extend about 2 meters and is necessary so that the rest of the sun shield can deploy. The sun shield membranes will be unpinned, and the telescoping sun shield mid-booms will extend, beginning with the port side, then the starboard. These booms will pull the aluminium-coated Kapton membranes out along with them, and the last deployment step will be the tensioning of the extremely thin membranes. During the second week after launch, Mission Control will finish deploying the telescope structures by unfolding and latching the secondary mirror tripod and rotating and latching the 2 primary window wings. But this isn't even the beginning, as it'll take 6 months for the telescope to become fully operational. In the first month, it'll take several weeks for the instruments to cool all the way down to the necessary temperature in the shade of the sun shield. This is because the cool down needs to be carefully controlled with strategically placed electric heater strips, so all parts shrink carefully, and any water trapped inside parts of the observatory can escape as a gas into the vacuum of space and not freeze as ice on the mirrors or detectors. All primary mirror segments, including the secondary mirror, will be unlocked and checked for free movement. Near the end of the first month, there'll be another mid-course maneuver to place the telescope into its optimum orbit around L2. In the second, third, and fourth months, optical checkouts will occur, and using the fine guidance sensor, the James Webb Space Telescope will be pointed at a single bright star to demonstrate that it can acquire and lock onto targets with data taken mainly from the NIRCam instrument. However, the primary mirror segments will not have been aligned at this point to work together as a single mirror, so there'll be up to 18 distorted images of the target star. Mission Control will then start the long process of aligning all the telescope optics and aligning all the mirror segments one at a time, including the alignment with the secondary mirror. This process will take a few months to complete, and by the time it's done, the cool-down process will end and the onboard cryocooler with the liquid helium will start running at its lowest temperature, and the MIRI instrument can start collecting data. Finally, during the 5th and 6th months, calibration of all onboard scientific instruments will be done while looking at targets, and the telescope will demonstrate the ability to track moving targets like nearby asteroids, comets, moons, and planets in our own solar system. At this time, NASA will make early release observations after the commissioning is complete. These will showcase the abilities of the observatory. Science operations will begin, and we're going to be very surprised at what the telescope is going to discover. The main science goals of the telescope are to search for the first galaxies and detect the very first stars that formed right after the Big Bang. During this time, the universe was only 1 or 2% of its current estimated age of 13.8 billion years, but we had no idea what it looked like, and we're about to find out. One of the most exciting things is that the James Webb Space Telescope will also be able to detect the presence of planetary systems around nearby stars from their infrared light, and it might just be able to see very young planets being formed. The Webb telescope will not have the resolution to see any details on the planets, but it will be able to measure the size of planets and able to see starlight that passes through the planet's atmosphere, measure its constituent gases, and determine if there is liquid water on the planet's surface. And yes, the telescope will be able to observe everything in our solar system that's further from the Sun than the Earth, including the dwarf planet Pluto and other Kuiper Belt objects. By studying our own solar system, we'll be able to test theories on how our solar system formed. is going to be a very exciting time because the Webb telescope is also going to observe Mars, Jupiter, Saturn, Uranus, Neptune, the moons around these planets, and comets and asteroids. And for the record, all of Webb's images and discoveries will be made available to the public, the same as the Hubble telescope. The only thing left now is for the scientific world to wait and watch the telescope go into space and hope that all operations and maneuvers go as planned. However, just recently, the James Webb Space Telescope has had yet another delay. Technicians were preparing to attach the Webb telescope to the launch vehicle adapter, which is used to integrate the observatory with the upper stage of the Ariane 5 rocket. But a sudden, unplanned release of a clamp band, which secures Webb to the launch vehicle adapter, sent a vibration through the observatory. Now NASA wants to be sure that those vibrations didn't cause any damage, so now the launch date is set for December 22nd, 2021. If all goes well, humanity is about to witness things never seen before. So make sure you stay tuned here to stay up to date on everything space related. We hope you enjoyed the video. Thanks for watching.